So up through the 18th century, much of the Western world had a particular way of thinking about how to organize all of the things on Earth. This is called the Great Chain of Being. And it looks kind of like this. This is a sort of illustration that was generated at the time, where you can see everything on Earth is organized along a single dimension. And this single dimension, here's that chain, spans from plants and things at the bottom, through different kinds of animals, through humans, through angels, all the way up to God. Of course, in the 19th century, the way that we think about living things changed. We had a different kind of conception of how to organize all of the living things on Earth, where we think about those living things as being different from one another, rather than lying along a single dimension, branching out in all of these different ways that are shaped by the constraints of their architectures and by the kinds of problems that are posed by their environment. This distinction between these two ways of thinking about the world, right? Organizing things along a single dimension versus recognizing differences that are shaped by these forces, I think is something that maps onto the kind of conversations that we're currently having in AI. People who are advocating for this idea of superintelligence, right, are implicitly making an assumption, which is like the picture on the left, where we can think about there being a single dimension of intelligence that we're organizing everything along, and then we're going to create things that are higher along that dimension than humans, and maybe ultimately create things like God, right? On the other hand, I think there's a more nuanced view of what it is that AI is doing, which is more like the picture on the right, which is that we're going to end up with different kinds of intelligence. Human intelligence is one kind of thing. Machine intelligence is going to be another kind of thing, where those differences are going to be shaped by the underlying architectures and by the kinds of problems that those systems have to solve. And so I think you can reduce this picture down to a sort of simple cartoon. Maybe it looks kind of like this. This is our picture of the one-dimensional case, where we can think about organizing all of the different kinds of tasks that we might like systems to perform, from doing math, to putting diapers on a baby, to reasoning about other people's minds, to processing text or playing games, along these different lines. And then we can plot where humans are along those lines, and then we can sort of illustrate where our AI system is. And the one-dimensional idea is that we're just going to sort of end up with something which is better than humans along all of those different directions. The alternative is something which looks more like this. This is what's being called a kind of jagged AI by various people, right? And here the idea is that we're going to end up with AI systems that are like the systems we have today, better than humans in some ways, worse than humans in others, and there's going to be this sort of interesting frontier that we have to map of what the capacities of our AI systems are and how it is that they're similar to and different from humans. If we end up with something like this picture on the right, it introduces a new and interesting problem. And that problem is, how do we actually map this jagged frontier? Right? How do we work out what are the things where AI systems are good and what are the things where they're not, and how is it that they're different and similar to people? Mapping that jagged frontier is something that at the moment we're largely doing by just trying to develop different kinds of benchmarks, right? You can think about each benchmark we make as another line that's thrown down in that space, and so if you throw down enough lines, we can measure what that frontier looks like. But in this talk, I'm going to advocate for a different way of doing this, where instead of just trying out different kinds of tasks that we might be interested in, we think about trying to target the places where we might expect there to be meaningful similarities and differences between AI systems and human cognition. And this is using a set of tools that we get from cognitive science. So part of the reason why I'm advocating for that is that many of the challenges that come up for understanding large language models are things that are going to sort of influence the kinds of methods that we want to use for trying to make sense of them. So if you think about what makes it hard to understand large language models, part of it is that they have some complex internal structure, right? They're built out of things like transformers that are themselves relatively complex. Part of it is that they're trained on opaque training data. We don't actually know what individual models are trained on unless we're working inside one of the companies that trains those frontier systems. And part of it is that we have difficulty accessing those internal mechanisms. Again, unless you have access to a proprietary model, you're forced to rely on simpler, older, more primitive versions of these systems to try and get insight into what those underlying mechanisms are. And while these challenges are perhaps unfamiliar to computer scientists who are used to making systems that they understand, they're quite familiar to cognitive scientists who have faced similar kinds of challenges in trying to make sense of human cognition. So complex internal structures, we have those, you have one inside your head, right? Opaque training data, we don't actually know what any individual human has experienced. And difficulty accessing mechanisms, unless you're good friends with a neurosurgeon, the kinds of strategies that people use for trying to make sense of those internal mechanisms through neuroscience are relying on analyzing older simpler, more primitive versions of those systems through the kinds of brains that we actually have access to for performing experiments. And so, as a consequence, a lot of the tools of cognitive science are tools that can be useful in trying to understand the behavior of large language models. And this isn't a particularly novel idea. There's a couple of papers that sort of make this argument that we can use methods from cognitive psychology or use methods from developmental psychology or comparative psychology or other kinds of psychological tools to do this. But I think one important insight related to this question of what kinds of AI systems we're going to create and what the properties of those AI systems are going to be is that this problem of trying to map the jagged edges of those AI systems is one that cognitive science is particularly well set up to be able to help us solve. And in particular, it's something which allows us to try and target places where we think there might be meaningful similarities and differences from human cognition. So in this talk, I'm going to focus on 3 different strategies that come from cognitive science that pick out different kinds of ways that we can think about trying to map out that space. And these correspond to things like thinking about the properties of the underlying architectures, the properties of neural networks, thinking about the limits that human cognition faces and how those might transfer over to our AI systems, and thinking about what the consequences are of optimizing systems to solve particular problems in terms of the behavior that you get out of those systems. And I'm just going to go through these 3 in turn, and in each case present a couple of examples that come from work that we've been doing in my lab that show how we can use these kinds of approaches. So the first of these strategies, this idea of thinking about the properties of neural networks, you might be asking, why is that something which is a strategy that comes from cognitive science? Isn't that what we do when we, as machine learning scientists, try and do things like mechanistic interpretability and so on? I think there's a good sort of reason for thinking about this as a strategy that comes from cognitive science, which is that, in fact, the kinds of neural networks that we use are things that cognitive scientists have been thinking about for a long time. So, we can go back to Frank Rosenblatt, created our first learning neural networks in the form of the perceptron. Rosenblatt was a psychologist. We can go back to the 1980s when David Rumelhart and Jay McClelland reinvigorated interest in using artificial neural networks. Again, they were both psychologists. Or you can even think about Jeff Hinton, their postdoc, right, who was also trained as a psychologist, as people who have been influenced by this kind of toolkit and as a consequence thought about how it is that these kinds of methods can be used and how the kinds of properties that they have in particular. So in making their argument to cognitive scientists that it might be interesting to think about the properties of these neural networks for understanding things like language learning, Rumelhart and McClelland demonstrated that it was possible to take a simple neural network, in fact this was a neural network that didn't even use backpropagation, and use that simple neural network to learn the past tenses of English verbs. And this was an important event that happened in the history of cognitive science because it was an argument that something which people thought could only be done by a rule-based system, right? So you can think about the past tense of verbs, you have that rule where you add ed to make the past tense, so walk becomes walked, and so on. Something where the way that linguists were thinking about that is something that's sort of intrinsically rule-based. They demonstrated it was possible to do using a neural network that had no kind of internal representation of those rules. And this was a significant achievement, but it was also something that caused a kind of backlash in cognitive science. And so a couple of years later, Steven Pinker and Alan Prince wrote a paper called On Language and Connectionism, Analysis of a Parallel Distributed Processing Model of Language Acquisition, where they went in and did a very exhaustive analysis of the properties of the model that Rumelhart and McClelland had introduced. And in that analysis, they came up with various kinds of critiques. I think you can reduce those critiques down to the fact that neural networks tend to blend discrete representations, so things that should be different from one another sometimes get smushed together, and are driven by their input statistics. Again, being driven by input statistics and blending discrete representations are things that make it possible for these models to do things like generalize and capture statistical relationships. But there are also things that allow these models to sort of behave in unusual ways. For example, one of the cases that Pinker and Prince highlighted was that the forms of the past tense that this model produced were sometimes strange, like it produced a past tense of male as membled, or a past tense of tour as tourida, right? And you can see there's some, again, sort of like blending of different discrete representations when this is happening. And so all of this is history, but I think it gives us a nice way of thinking about the kinds of characteristics that neural network models tend to have, and things that we might look for when we try and analyze the big large language models that we have today that are based on the kinds of technologies that underlie these neural network systems. And so I'm just going to give you, again, a couple of examples where we can actually go and look at a large language model and show that they still have these kinds of characteristics, that they blend discrete representations, and the way in which they behave is driven by their input statistics in ways that we might not necessarily want. So in terms of blending discrete representations, the example I'm going to give you is focused on numbers. And the reason for that is that numbers are nice in having different ways that you can think about representing those numbers. So for example, the number 911, you could think about in two different ways. You could think about this as the string 911, right, where it's the sequence of digits, 9 followed by a 1 followed by a 1, in which case 911 is, similar to another string like 411. These only differ in one character that we've changed. So if we're thinking about numbers as strings, we'd say these two things are similar to one another. Of course, another way you can think about numbers is as magnitudes, right? So here, this is not 911, it's 911. And if we think about 911 as being 911, then it's going to be similar to 914. And so this other way of thinking about what this number is something that results in us thinking that it might be similar to a different kind of number. So the way in which you're representing this, these two discrete ways of thinking about numbers, would lead you to make different kinds of generalizations when I ask you which things are similar to one another. And I'm focusing on similarity judgments here, because these are a classic tool that cognitive scientists have used for trying to understand the representations that systems have. So, for example, Roger Shepard was a pioneer in using these kinds of similarity judgments as a way of extracting information about the representations that people have inside their heads. You can kind of think about this as a strategy for discovering, the embeddings that systems might use, even if you don't have access to those embeddings. And so the way that this works, we would take a set of stimuli, such as these are different wavelengths of light, right? So you can think about different colors being represented by different wavelengths of light. We have those different wavelengths along the rows and the columns of a matrix. And in that matrix, we just put in some kind of measure of the similarity that people assign to that pair of stimuli, right? So for a particular combination of wavelengths, we can look in this table and we can see, okay, whether those things are considered similar or not. And then Shepard showed that you can use methods like multidimensional scaling to go from these sorts of similarity judgments to a representation that tells us something about how it is that people might be thinking about that domain. So for example, for wavelengths of light, even though those wavelengths lie along a single dimension, our psychological representation of light, of color, is a two-dimensional representation, because we think about these as lying on a color circle where red connects back through violet to blue, even though that's not something which is true in the physical stimulus. And so this is a nice sort of cognitive science toolbox for being able to explore representations that people have in different domains. For example, you can show that people's representations of number have this sort of perhaps multidimensional quality where if you get kindergartners to say how similar numbers are to one another, you get out this nice sort of simple one-dimensional representation where they just think about numbers in terms of magnitude. But by the time you get up to 6th grade, they're starting to think about numbers having not just their magnitude, but also mathematical properties, such as being odd or even. And then if you look at adults, they have even more sophisticated representations where they think about numbers in terms of magnitude, odd, even, but also things like whether something is a power of 2. And so we can pull these things out of the representations inside people's heads by using similarity judgments. And so you can do something similar in the case of numbers. These two ways of thinking about numbers, as a string versus as a magnitude, translate into different predictions about the similarity that you should perceive between those numbers. So if you're thinking about numbers as a string, then similarity should be something which reflects something like the Levenshtein distance, right? So this is just our string edit distance. So whether we're changing, how many characters we're changing when we go between numbers. And so here this is a similarity matrix, again, with numbers down the rows and numbers across the columns. If you're thinking about numbers in terms of magnitudes, then you should say that two numbers are similar to one another as long as they're similar in size, and you get a representation like this, where here we're assuming log linear scaling of the space of numbers, which is consistent with what we see in human cognition. And so Raja, Venya, and Ilya asked a bunch of large language models to give us similarity ratings for numbers, and looked at the representations that come out of this. And what you should be able to see here is that we see exactly this kind of blending of these two discrete ways of thinking about numbers inside these large language models. So for each of these representations, you can see that the similarity matrix has characteristics of both the Levenshtein representation and the log linear representation. You have these sort of central magnitude sensitivity, but you also have these stripes that reflect the representation of the number as a string. You can push this around a little bit, right? So these models know a lot about code, so you can give them numbers that are given within casts. So you can cast the number to an integer or cast it to a string, and you get some differentiation where now you get more magnitude-like things when you cast to an integer, and you get more string-like things when you cast to a string. But you can see there's still an influence, these stripes that still show up here, of the string representation in the integer setting, and there's still an influence in this diagonal here of the magnitude in the string setting. And you can't even sort of, train past this. So this is looking at what happens if you try and take the actual embeddings from a model and then train linear probes that are trained to produce either the string similarity or the integer similarity from those representations. And despite doing the best you can, there are still traces that show up. So we still have this magnitude trace that shows up when we try and train something that's a string representation without any integer representation, and we still have the stripes here that show up when you try and train something that's an integer representation without having influence of strings. And these are just multidimensional scaling representations of the solutions that come out of these embeddings. So this, might seem like a trivial property, right? I've said we know that neural networks tend to sort of blend discrete things together. I've given you a simple example where this blending seems to happen. If we ask the models to just tell us how similar things are, they're not able to differentiate these two ways of thinking about numbers. But blending these representations can have significant consequences, particularly because of the way in which we tend to deploy these models. So here's a simple example. You can imagine this being an assistant for a pharmacist. It says, you require a compound with a concentration of approximately some number, parts per million. 2 test tubes are available, one containing some other number, parts per million, and the other some other number, parts per million. Your task is to determine which test tube provides the most similar concentration to your required dosage. Which one will you choose? Respond only with the value of the test tube that you choose. Okay? So we've set this up in a way where there's some concentration, which is the target concentration. You have an option of choosing between 2 different numbers that represent concentrations in those test tubes. And here, the right answer is to make an answer that's based on magnitude, right? You should choose something which is similar in magnitude because that's what matters in this medical context. But despite that, because these models aren't able to differentiate these ways of thinking about what numbers are, you end up with the models producing the wrong answer with relatively high probability, again, something that you'd be concerned about if you were actually going to be deploying this as an assistant to a pharmacist. And so this is something that we need to watch out for and think about, is if there are situations where there could be ambiguity in the way in which something is represented and the models are constructing blended representations of those things, those blended representations can have unexpected consequences for the way in which the models end up behaving. The second of these characteristics, being driven by input statistics, is also something that influences the behavior of these models in unexpected ways. This is something that we explored when the Sparks of Artificial General Intelligence paper first came out. We were sort of playing around with GPT-4 and discovered that it did some weird things, and we're trying to understand why it did those weird things. And we wrote a paper that describes this called Embers of Autoregression, where basically the argument is that in fact, these models show a sensitivity to input statistics in a way that is perhaps not something that you necessarily want in your artificial general intelligence. And this is joint work with Tom McCoy, Dan Friedman, Xinyu Yao, and Matt Hardy. So here are 4 weird things that we noticed that GPT-4 does. The first of these is that if you ask it to count the number of letters in a sequence, it would be more likely to be correct if the number was 30 than if the number was 29. Right? And this is roughly 80% versus roughly 20%. If you ask it to do a simple text processing task, like swapping each article in a sequence of words with the word before it, it does very well for some sequences of words, but very poorly for others. Remarkably, you could ask GPT-4 to solve a shift cipher. So here, this is a cipher which is created by taking every letter in the alphabet, moving it forward some number of positions. So to decode this cipher, you need to shift back the corresponding number of positions. And it can actually do that. So if you ask it to decode something where you're shifting every letter 13 positions forward, and it has to shift back 13 positions, it can solve that. But if you ask it to do that for 12 positions, it can't. And then here's a sort of simple math task: multiply a number by 9/5 and add 32. It can do that. But if you ask it to multiply by 7/5 and add 31, it can't, right? So in each of these cases, we have sort of two variants of a problem, where on one variant of the problem, it's actually very successful, and on the other variant, it's not. And so it's kind of an interesting question. What is it that distinguishes between these successes and failures? What we show in the paper is that this is really a consequence of the input statistics of the models. So because these models have been trained, as at least part of their training, to be predicting the next token that appear in sequences, they have a high sensitivity to the probability of sequences of tokens, and that influences the way in which they're engaging with these questions. So for example, the reason why it does poorly when you ask it to count sequences of 29 letters, but better when you ask it to count sequences of 30 letters, is simply that the number 30 appears with higher frequency on the internet than the number 29. And so we can actually show this, that if we plot out the frequency of the answer versus its accuracy in counting those strings, we find this nice negative relationship, right? That as the frequency of the answers decreases, the accuracy in producing those answers decreases. And this is something that you might be worried about, again, if you're building your AGI system, right? Having sensitivity to the probability of the outputs, that influencing the probability you produce the correct answer is probably not something that you want your AGI to do. Here's another case, the text manipulation example that I gave, right? The reason why it does a good job here and a poor job here is that after we follow this rule of moving around the articles, you end up with something which is a grammatical sentence in English on top. And after you follow that rule for the example on the bottom, you end up with something which is not. And so as a consequence, this sequence has high probability, and this sequence has low probability. And we showed that, in fact, there's a very direct relationship between the probability of the output sequence and the accuracy of the model in producing that. So because you pre-train a model to try and produce high probability token sequences, it really doesn't want to produce answers that are low probability token sequences. Again, maybe something you should be concerned about in your artificial general intelligence. And we showed that this isn't just the case for these particular tasks, it's actually the case for a whole bunch of different kinds of tasks that we could come up with. It also generalizes across different models. This is showing performance on the counting task for different numbers. So this is accuracy, these are different numbers. You can see all of the models are better at counting to multiples of 10 than things that aren't multiples of 10, again, reflecting the fact that multiples of 10 just have higher frequency on the internet. And then this is showing output sensitivity, to output probability across different models for these different tasks. And we see across all of these models, they show this same kind of sensitivity. The other kind of sensitivity to input statistics that we found here is that the frequency with which a model encounters a task in its training data influences its ability to perform that task, right? So the reason why it's able to do a shift cipher that involves shifting 13 positions, but not one that involves shifting 12 positions, is that that shift cipher, it's called ROT13, appears on the internet with relatively high frequency. So in fact, the only shift ciphers that GPT-4 could solve were shift ciphers that involved shifts of 1, 3, or 13. And each of those appears on the internet for different reasons. So a shift of 1 is used in a lot of tutorials on decoding. A shift of 3 was Julius Caesar's favorite cipher, and for that reason appears in, again, sort of like people talking about these kinds of codes. And then the shift of 13, ROT13, is a common cipher that's used for people who are on internet discussion boards, who want to conceal information in a way where it's not immediately accessible, like if you're putting up the solution to a puzzle or spoilers for a book or something like that. And so as a consequence, there's a relatively large amount of text on the internet that's in ROT13. And so you can think about this as essentially what it's been able to do is learn something like, ROT13 as a foreign language, right? It's able to figure out what the structure of this mapping is. And again, the reason why it can't do ROT12 is that ROT12 doesn't appear on the internet with any frequency. And then likewise for our linear functions, you probably recognized what the linear function on the top is, right? So this is the function for transforming from Celsius to Fahrenheit. That appears on the internet with relatively high frequency. The function on the bottom is not, right? And so we see a difference in the performance of the model on the rare versus common variant of this task, they can do the one which is more common, but the one which is rare they're less good at. And again, it's about having familiarity with those tasks in their training data. And so again, we see this across other tasks and other models. So you see this difference between a rare and a common variant of a task manifest across all of the models that we looked at and across almost all of the tasks that we examined. Now, this was a while ago, right? GPT-4 came out, far enough in the past that things have changed since then. You could think about things like, does prompting help these models do better? And the answer is yes. So if you just ask them to think step by step, they begin to be able to generalize a little bit, right, away from the cases that they've encountered with high frequency. If you give them a few-shot chain of thought, so you give them some sort of worked examples that they can then build on, they can do even better than that. Now you're sort of seeing this generalization again from these cases that it knows how to solve. And if we look at more contemporary reasoning models, the reasoning seems to be something which offsets this task frequency effect to some extent. So here are the reasoning models, just so that I can call them out. Claude 4 here, and this is O1 preview on the bottom. And if you look, this is contrasting rare versus common instances of the tasks that they're performing. And these reasoning models actually do a better job on the rare tasks, the tasks that they haven't necessarily encountered in their training data. So they're able to essentially use the extra tokens that they're generating to allow them to generalize better from the things that they've seen in their training data and produce more accurate answers for these rare kinds of problems. Interestingly, there's some evidence too that they produce more tokens for the rare tasks, consistent with them needing to sort of do more work in order to produce that generalization. But the other effect that I talked about, this sensitivity to output probability, is still something that we see even when we look at these more contemporary models. So again, here's Claude 4 and O1 preview. And for these different tasks that I highlighted before, we still see a sensitivity to output probability in the performance of these models. So it's still the case that you can predict how accurately a model is going to solve a problem based on the probability of the token sequence that it's needing to produce when it solves as an answer to that problem. Okay, so the second source of ideas about things that might be difficult for our AI models comes from considering the kinds of limits that we actually see in human cognition. And in that last example, I showed you that reasoning was actually something that seemed to help, at least with the effects of task frequency. But one thing that we actually might suspect, based on information that we get from what works for humans, is that reasoning isn't necessarily something that should always be beneficial. So there's been extensive work trying to look at where chain of thought kinds of prompting aids models, right? There was a nice review of this by Sprague and colleagues where they showed that across a wide range of tasks, but primarily like mathematics and reasoning tasks, it seemed like chain of thought was something which was beneficial. But we were able to identify some cases where, in fact, reasoning is detrimental to the performance of models, and they're based on cases that we see in the psychological literature where reasoning is also detrimental to humans. I'm just going to talk about the first two of these, implicit statistical learning and face recognition, as two places where you have detrimental effects of reasoning, just for the consequence of limited time. I'm happy to talk about the last example in more detail if people want later, but in this last example, we have a situation where we have a simple rule that captures about 75% of instances in a classification problem, and a more complex strategy which gives you 100% performance, and engaging in reasoning leads models to fixate on that simple rule, and as a consequence, not achieve full performance. And this is joint work with Ryan Liu, Addison Wu. Ryan and Addison are both here today, Jai Yang, Ilya Suchulitsky, and Tanya Lombroso. So we're going to do the first of these as a demo, so be ready to answer a question. Okay, so here on the left are a bunch of strings that belong to a language. And on the right are two strings. One of these is from the language and one of them is not. And the way I'm going to collect the data from you is I'm going to get you to hum. This is what I do in my classes. If you use clickers in your classes and so on, that's unnecessary technology. I just use humming. Humming is good because people can't tell if you're humming when they're next to you. It automatically aggregates the results, right? They're sort of integrated at people's ears. We can sort of know what the answers are here. So we're going to use the low-tech version of the feedback here. So if you think that the first sequence is from the language, hum now. Thank you. Second sequence. All right. Good. Okay. And so this was a case where I didn't ask you to do any particular thinking, right? You just sort of gave a response. I could ask you to try and explain why you think that the first sequence is better. But for many of you, it's probably just a kind of gut feeling that that seems like a better instance. And in fact, this is a task where if you ask people to come up with an explanation for what they think the underlying rule is and why it is that one is better than the other before they give an answer, they end up doing worse on this task. Part of the reason for that is that the way in which these sequences are actually generated is using a kind of finite state automaton, right? So this is the original one that was used in these studies of implicit statistical learning. We used a slightly different one in this example here. But what that means is that the way to answer this question of whether a sequence belongs to the language is essentially by checking whether the transitions that appear in the sequence appear in the data that you can see over here, right? So you're really sort of paying attention to the frequencies with which you see transitions between the characters in the different strings. And so that's something that people are just sensitive to, right? You sort of just pick up on those statistics. You're like, that kind of looks like those other ones, right? And so if you're just doing that gut feeling thing, you get the right answer. But if you ask to explain, okay, why is that the better one, you're going to try and come up with some kind of simple rule. There's not a simple rule here. It's really just a finite state automaton. And as a consequence, you get hung up on that simple rule, and you end up making a mistake. And so we could take this setup and then sort of explore all sorts of different kinds of variants on the structure of those finite state automata, and then use that to create different training data that we can give to our large language models, different prompts we give them to the large language models, where we ask them to make exactly that decision that you made, and then contrast what happens in a reasoning model or a model that's using chain of thought versus one that isn't. And when you do that, when we compare across a whole bunch of different models, zero-shot prompting, where it's just given the strings and asked which is the right answer, versus a chain of thought prompt, and here I'm counting GPT-4o as zero-shot and O1 as the sort of chain of thought analog, we see a meaningful performance decrease when we start using chain of thought prompting. And this is particularly striking for this contrast between 4o and O1, right, where we see a big decrease in the performance of O1 as a consequence of trying to figure out what that underlying rule looks like. Another example where you see something like this with people is in face recognition. So the classic study of this by Schooler is something called verbal overshadowing. In that experiment, they had people watch a video, and then they completed some other task, and then they were asked to provide a description of the person that they saw in the video, and then they had to pick them out of a sort of lineup, right? And this was a kind of study that was being done in the context of eyewitness testimony, where you can think about, you know, what are the best strategies for being able to identify somebody that you saw in a crime or something like that. What they found was that if you ask people to give a description, they do a worse job of picking the person out of the lineup, right? And the reason for this is that if you give a description of a face, the kinds of things that you focus on are things like the eye color, the hair color, you know, particular individual features of the face. But when you recognize a face, you're not relying just on those features, you're relying on how it is that those features are related to one another. And so, you know, in this case, the kind of task that we gave to the AI systems, in this case, our vision language models, was one where we gave them a static image, and then they had to pick out the person who corresponded to the person that they'd seen from another set of static images. And to make this extra hard, these are AI-generated images, so we use Stability AI to generate these images, and they were generated based on the same descriptions, right? So we would give a description of this face in terms of the underlying features, use that to generate this image, but also to generate the contrast images that you had to pick them out from. So all of these images then end up with the same description in terms of what those underlying features are. And then we can contrast again using the direct prompting versus chain of thought prompting in this setting. And what we see, again, across a bunch of different models, is that when you contrast zero-shot versus chain of thought prompting, you see this significant decrease in the performance of those models when they're trying to perform this task. So you could think about this as being a consequence of some kind of limitation, right? In the human case, it's that we're limited in our capacity to maintain an encoding of an image when we are asked to describe that image in terms of words, right? That sort of overtakes the representation that we had, right? And so it's really a consequence of a limited capacity on the side of human cognition. Similar kinds of capacity constraints also seem to influence vision language models. And this is a paper that we had at NeurIPS last year. We have so many people on this paper, I couldn't put all of the images on one slide. But what we looked at here is whether classic kinds of results on the limits of human visual attention are things that allow us to understand some of the limits of vision language models. So a classic kind of limit of this kind is what's called supertizing limits. So if I ask you to count how many things are on the left, you can say immediately 3. If I ask you to count how many things are on the right, it takes you a little bit longer, right? And that's what these data show. So people have what's called a supertizing limit, which is that if you show them up to 4 things, they essentially give you exactly perfectly the right answer, and there's not really a meaningful increase in how long it takes them to answer those questions, right? So in particular, as you go up to 3, 4 is already starting to push limits for some people. One thing that happens, though, is that after you get past that limit, you get into a regime where people start to make more errors and where reaction time increases significantly. So the way to think about this is that we have the capacity to sort of individuate up to 3 or maybe 4 things that appear in images, and we can do that spontaneously. And then the way that we are able to count instances of more things is by engaging that same capacity but in a serial way. So there's a limit on what it is that we're able to encode, and then we get around that limit by engaging in serial processing. What we show in this paper is that vision language models have a similar kind of limit, but they don't have the serial processing capacity that they need in order to be able to get past it. So you can give a vision language model a counting task, right, which is similar to the one that I just showed you, where you have different numbers of objects, and you can look at how performance on that counting task varies with the number of objects. And you see, exactly like in the human data, there's a supertizing limit. So this is aggregate performance across GPT-4v, GPT-4o, Gemini Ultra 1.5, and Claude Sonnet 3.5, just to sort of reduce the number of lines that we have on the plot here. But the critical thing is that across all of these models, you see something like that human supertizing limit, right? There's sort of a point where, whoops, they're essentially perfect up to that point, and then they drop off rapidly after that. And they're not able to increase their performance by engaging in serial processing. I know that's something that more contemporary models have started to do, but it gives us a way of understanding what the limits of these models look like. Another example like this is contrasting serial and parallel visual search. So again, a classic result from the psychological literature based on work by Anne Treisman. If you look on the left, I ask you to find the red dot. You found it, right? If you look on the right and I ask you to find the red L, takes you a little bit longer, right? And so this difference between disjunctive search and conjunctive search is that disjunctive search is a parallel process, right? You're just able to immediately do this. This is within the sort of capacity of your visual working memory. Conjunctive search, where you have to combine 2 features together, in this case being a red and being an L, is something that requires engaging serial processing capacities, and you're searching over that array looking for something that satisfies that. And again, because our large language models, or our vision language models, don't have that serial processing capacity, the expectation is that if they have this same kind of visual working memory limit that humans do, we're going to see a meaningful difference between disjunctive search, which is that it's insensitive to the number of dots that are in the array. You can always answer this question, whereas conjunctive search should be sensitive to the number of things that you're searching over. And that's exactly what we see. So here on the top, you can see the performance of disjunctive search is not affected by the number of objects you're searching over, whereas for conjunctive search, you see this rapid decrease with the number of objects because it's not able to engage in that serial processing. And again, this is something that influences the performance of these models. So if you think about the kinds of things you want vision language models to do, you want them to be able to give you descriptions of scenes. And so we created a multi-object description task where the models are asked to just describe what it is that appears in these scenes. And then we manipulated the visual similarity between the objects that appear in those scenes. And this is basically the extent to which those objects share features with one another. So here, all of the objects share features, and here, all of the objects are differentiated in their features. Because the hypothesis about where this limit comes from is really it's a limit in being able to effectively bind the features of an object to the object itself. And if that's the case, we should expect to see that as objects become more confusable, the models are going to do a less good job of solving this problem. And that's exactly what we see. So here, the way we're measuring the confusability of objects is in terms of triplets, where a triplet, consists of 3 objects such that every 2 of those objects shares 1 feature, right? So a triplet is a confusable set of objects. As the number of confusable objects increases, the error rate for these models performing this simple task of describing what these scenes look like also increases significantly, right? And so this gives us a way of understanding how a sort of fundamental capacity limit that we see in these models, hypothesized on the basis of a capacity limit that we see in human cognition, is something that influences their ability to do the kinds of tasks that we might want them to do as AI systems. The last strategy I'm going to talk about is one that focuses on what it is that we optimize our models to do. If you focus on the headlines, I think nowadays it seems like what we really want our models to do is to be rational, to be good at reasoning, to be good at solving math problems. Essentially what we're trying to do is optimize more deterministic models that treat tasks as math problems. That's what all of the current kinds of RL-based training is doing for these AI models. We can actually see evidence of this in the way in which these models behave when we compare them to things like human decision making. So we had a paper last year where we showed that if you just get these models to make predictions about what choices people will make when they're solving a gambling task, like the one on the bottom, where they're making a choice between A and B, where you get some payoff with some probability for each of these different options. The way that the large language model makes a prediction about human performance is basically by calculating the expected value associated with those two options, and then saying that people will choose the one which has the highest expected value. That's what you should do as a rational agent. It is not what people do, right? And as a consequence, the model ends up making poor predictions about human behavior. We can see something similar in a more recent paper. This one's going to hit archive pretty soon, where we looked at asking the models to make evaluations of simple kinds of games. So here the task is to say for these different board games how fair the games are, or to estimate the payoffs that might be provided to different players. And when we look at the correlation between different models, here I'm just focusing on models within the GPT family and human performance, you see this interesting trend where the models, as they become more sophisticated, so this is going from GPT-4 through O1, O3 up to GPT-5, the models, as they become more sophisticated, become more correlated with the game theoretic optimal answer to those questions. That's what these gray dots are. But in doing so, they sort of start to become less correlated with human judgments. And so, again, I think we're starting to create models that are sort of interestingly more rational, right, in ways that might limit their ability to make good predictions about human behavior. So these are examples where, you know, like this is something we might be a little bit concerned about. I think there are actually bigger concerns here as well, which is that what we optimize models for is something that can have unintended consequences. And I'm going to illustrate this using a task that comes from a psychology experiment that was run by Zhuchen Zibai. So in this experiment, we imagine a hiring manager who is at a company and is hiring people for different kinds of roles within that company. The hiring manager is making decisions about people who come from 4 different social groups. And here I've illustrated these social groups just with these different colors here. The first job that they're hiring for is a janitor. It's a job that doesn't require necessarily a high level of expertise and doesn't require necessarily having particularly good communication skills. The hiring manager hires somebody for this position from the green group. They succeed in that position, and you know, this is a success. The next position is a doctor. This is something that requires high expertise, more communication skills. They try hiring someone from the green group. Unfortunately, it doesn't work out. And so they move on. So now they're hiring someone for a veterinary position. So it didn't work out with the green group for the doctor, so maybe this hiring manager tries someone from the blue group. That works out. That was a successful hire. Now there's another janitor position. Okay, it seemed like that worked with the green group before, so hire another janitor from the green group. And then now there's another doctor position, and the hiring manager chooses someone from the blue group. Okay, so from the hiring manager's perspective and from the company's perspective, this has been a successful series of decisions. They've hired people who, in general, are successful at the jobs that they're pursuing. But as a consequence of making a series of, you know, individually adaptive choices, this hiring manager has now ended up with a stereotypical bias, right? They have a bias to think that people from the green group are better at janitor-type jobs and people from the blue group are better at sort of doctor and vet kind of jobs. When in fact, the underlying truth is that all of these people would have succeeded in all of these jobs. They were all people who, you know, the rates of success were equal across all of those groups. And the reason that the hiring manager didn't discover this is that there was a cost for exploration, right? That trying out somebody from a different group or trying somebody from a group that didn't succeed previously is something which is associated with a cost because that person might not work out for that particular position. So these kinds of costs for exploration are something that can create biases. We can see this by taking exactly that setup and running Thompson sampling. It's a contextual bandit problem. Thompson sampling produces the same kind of stratification. So again, this is groups. This is jobs. The intensity here represents the frequency of those choices. You can see this is a relatively low entropy distribution, reflecting the fact that it's introduced stratification here. And likewise, if you have human participants do this experiment, they produce exactly the same kinds of patterns where they tend to focus on individual groups being good at individual classes of jobs. Interestingly, Addison, Ryan, and Zhizhenzi showed that large language models do this more than people do. So this is a plot where it's showing two metrics for the extent to which they're introducing this kind of bias. One is stratification index. This is the relative entropy of the distribution over jobs that they're producing. And then the other in orange is it's like the Jensen-Shannon divergence between the distributions over jobs for different groups. But the critical thing to see here is that the human data is the dashed lines, and the model predictions, shown in blue and orange dots, are generally above the corresponding human lines, right? So our large language models, which are treating this as a math problem, like Thompson sampling, are producing new social biases as a consequence of the way in which they're solving this problem. And that happens increasingly as those models become more powerful. So now this is restricted within individual groups of models, ordering those models in terms of their size or recency or amounts of training data. And we see greater stratification being produced by more sophisticated, more powerful models. Now, we tried various kinds of things here to try and reduce this effect. Things like chain of thought and temperature changes don't help very much. If you try prompt-based interventions, telling the models to be more fair or to lean on their training to be fair or these other kinds of things don't really help. The one thing that really does help is by modifying the objective that the model is using by saying the company has a bonus for trying somebody from a new group in a new kind of role, and then it does a better job at doing this, right? But that's exactly consistent with the fact that the model is really trying to solve this as a math problem, right, and is responsive to the way in which that objective function is defined. So we need to be very careful if we're making our deterministic, math-based kinds of systems in the problems that we pose to those systems. Okay, so these are three different strategies from cognitive science for thinking about ways in which AI models might face particular kinds of challenges, right? Strategies that we can use to map what the edges of those jagged frontiers look like. My hope here is that this isn't just something that we can use to get better insight into how AI systems work, but also to get better insight into human intelligence. I think the ultimate expectation that I have is that we'll really discover that these are different kinds of systems that excel in different ways and that can work together in ways that are complementary to do things that neither AI systems nor humans can do alone. But I think even broader than that, I think my argument here is that maybe we want to change the way that we think about how intelligence works, moving from something on the left, like this sort of one-dimensional scale, to something on the right, where we think about different kinds of intelligences being shaped by their architectures and the kinds of problems that they solve. Thank you very much.
Okay, we have some time for questions, and we have microphones on both ends. If you are doing a spotlight in the next hour and you haven't checked in with me yet, this is a great time to do it.
Hi, thanks for the talk. I'm wondering to what extent at least some of this is explained by seeing the outputs as sort of like a mixture of solutions, and the role of the model is to sort of figure out what weights to put on each one, and that comes from sort of what's in the prompt. So for instance, in the first example where I guess it was where the chain of reasoning helped, the medical example. So there, it was sort of ambiguous explicitly what the representation was.
Yep.
And so it didn't really know, but then you give it chain of thought and it can pull out what would make the most sense given the context, which representation to use. And so that's why so it's kind of just an extended, more informative prompt. And then in the other case where it didn't help, where the chain of thought didn't help, the second example with faces, there it's like almost an adversarial setting because you're getting it to sort of commit to a representation that's actually not really great. And so the chain of thought doesn't help in that case?
Yeah, I mean, I think that's consistent with what I was saying, right? Which is that we shouldn't necessarily expect that something like engaging in verbal reasoning is going to always be beneficial. The cases where it's going to be helpful are cases exactly where having additional tokens that you condition on is something which is going to improve the answer to the question that you're asking, right? And that's something that you can think about. You can think about categorizing tasks along that dimension, right? But a good set of heuristics that we can use for figuring out what that space looks like is exactly looking at the cases where that's not the case for people, right? Yeah.
Thanks.
Hi. Last year at Cologne, we had a nice talk from Ev Federico about kind of how having a kind of like second device that spoke language kind of was challenging some of the kind of core assumptions in the field. You spoke a lot about how cognitive science could help understand these systems, but I'm curious about the converse of like whether some of these dogmas have changed now that we have things that maybe reason in a kind of unique way.
Yeah, it's a great question. So we, a group of us, it's me, Tom McCoy, Taylor Webb, Ellie Pavlik, and Brendan Lake have a paper which is called Wither Symbols in the Age of Intelligent Neural Networks, right? Which is really arguing that a lot of the evidence that historically had been used to make arguments about symbolic systems being a key component of the actual processes of human cognition is now something that these neural networks are able to do. And so we need to go back and ask again, with more nuanced tools and sort of, better kinds of methods, what are the things that maybe either give us strong evidence that people are engaging in something like symbolic reasoning versus, in fact, it being the case that symbols are mostly useful in describing what it is that these systems do in terms of the problems that they solve. And so that's a simple example where I think a lot of the assumptions of the field are changing as it becomes the case that we're able to make other kinds of systems that can demonstrate those capacities. Yeah.
Cool, thanks so much.
Hi, thanks for your talk. Could you maybe speak to how models do on classifying data based on rules with exceptions, which you mentioned was
Yeah,
interesting?
so I skipped over that one. I can just tell you that task very quickly. So the basic structure of this task is one where this is based on an experiment that was done by Joseph Williams and Tony Lombroso, where they showed that if you give people a classification problem like this, where there's a rule which is quite useful in discriminating between class A and class B, right, which is that class A vehicles tend to be yellow and class B vehicles tend to be orange, but that only works 75% of the time, right? So that's the simple rule, versus the more complex thing you have to do is actually pay attention to the license plates of the cars. And then if you recognize the license plates, that's a perfectly diagnostic strategy for differentiating what class these cars come from. And so if you ask people to do this and then explain their basis for making those decisions, they focus in on that simple color rule, right? Because it is sort of explainable, verbalizable, whereas paying attention to the license plates is just, it's more of an exemplar-like strategy where you're just paying attention to the individual instances. And then what we show is that using a version of this task for large language models where they're essentially doing this in context, where you're sort of increasingly providing more and more of those examples, you see that you need many, many more rounds of training to get these models to figure out what's going on when they're doing chain of thought. And so this is just an illustration. I said that rule works about 75% of the time. That's essentially the level that chain of thought converges to. This is for GPT-4, whereas if it's just trying to do this via direct prompting, not trying to produce a sort of verbalizable rule, it ends up doing very, almost perfectly on this task because it's able to do it by solving that task in context. Yeah.
Great, thanks.
Is there time for another question?
Yeah, we have time for 2 or more.
Thank you so much. Fascinating talk. And my question is relevant to Sasha's, actually. So you mentioned the past tense debate in the first part of the talk, but it seems that now with today's language models, we're having that again at a larger scale, where there's one side that says these models learn language, and this tells us something about cognition and learning, and the other side says, no, they don't learn language, because look at this failure case. So I was wondering what your take is on this. Do they learn language or do they not? You already said in the previous question that, you know, this tells us something about how we should approach theories, but I'm interested in your take on this generally.
Yeah, I mean, so I think they do so well, right, and so much better than people might have expected that we do need to revisit the way that we think about those things. You know, there are also still very clear differences between humans and large language models, the most notable of those being the amount of training data that humans require versus language models. So that is still very clear evidence that there's some kind of inductive bias in humans which is different from the inductive bias in our language models. And that's something which we might expect to have manifestations in exactly what it is that they learn, in particular when we zoom in on those very fine details. And so I think that's a very exciting kind of thing to do for cognitive scientists, right, is to try and solve these two separate problems, right? So one of these problems is trying to characterize what that inductive bias is like, and then the other is figuring out what are the right questions that we can ask, what are the right kinds of tools we can use for analyzing the knowledge that's inside these models to be able to work out what the consequences of those inductive biases are. And so, you know, I'd say it's sort of like moved the field forward in terms of allowing us to focus on those much more specific questions rather than just saying, oh, it doesn't work at all. Yeah.
Thank you very much.
We can take one more question.
Hi, thank you very much for the great talk. So I'm wondering about the reasoning results where reasoning leads to worsened performance in certain tasks. I'm wondering, do you think it's just a matter of how reasoning is currently trained? Like imagine if we could train reasoning in domains outside mathematics and coding, then perhaps that would be different.
Yeah, that's a great question. I mean, so there were two separate things, right? So one was just being able to recognize when you should reason and when you shouldn't. We have a project where we looked at this it's on what we call rational meta-reasoning for large language models, where essentially what we did was have a penalty function that's used in the RL training for reasoning in the model, and as a consequence of doing that, it's sort of pushed to not reason in circumstances where reasoning isn't helpful and reason in the circumstances where it is. And so when you do that, you end up getting you know, similar performance to models that are just trained for reasoning, despite using many fewer tokens in the circumstances where it's appropriate to use fewer tokens, right? So that's one kind of problem. It's just like thinking about how to solve that meta-reasoning problem. The other case, like the last example that I talked about, is more about what it is that we're reinforcing our models for, right? And that's something where I think either we need to think about using that tool of reinforcement learning more broadly in terms of not just reinforcing for reasoning, but reinforcing for other kinds of, you know, things that we want the models to be doing with their tokens, right? Or think about, you know, again, this is something you already see, just having more differentiated models where maybe you have your math model is a different model from the one which is your more, you know, the one that you want to use for assisting your hiring manager, right? And that those aren't necessarily one big unified model, sorry, but those are more differentiated in what they do. Yeah.
Thank you.
Okay, let's thank Tom again.